Welcome to Mrs. D's Chemistry. In this video, we'll discuss the scientific method. Before any science experiments or studies are conducted, we need to be curious about an observation we've made about how the world works. If no one has made an observation or no one was curious about it, then it probably won't be studied. And this is because scientific studies can be very expensive and require lots of funding. So if we don't believe there's much of a benefit, it probably won't be studied. But once we do have a question about an observation that's been made, we can form a hypothesis, which must be able to generate a prediction. Then we can perform experiments and make more observations. When our new observations refute or falsify our hypotheses, as they almost always will, then we go back to our hypothesis and come up with a new hypothesis, or maybe multiple hypotheses, which then generate new predictions. And then we do more experiments. In this diagram, this is pictured as a circle, as we often stay in this portion of the scientific method for a very long time. Once we have a collection of hypotheses that haven't been falsified yet, this collection then begins to contribute to the body of knowledge, where a wider range of scientists from different fields begin using these hypotheses in their work. If on further testing, some of our hypotheses are shown to be false, we go back to the drawing board. If, however, our hypotheses continue to show consistent results, a large collection of hypotheses, possibly from many different fields of science, may become either a law or a theory. Notice that there is not an arrow between these two, theory and law. Theories do not become laws, ever. And laws are not greater or better or more accurate than theories. We could have just as easily wrote theory right here and law down here. A scientific law predicts what happens, while a theory proposes an explanation as to why it might happen that way. A hypothesis is one of the many possible answers to our beginning question. Your hypothesis must be able to generate a prediction in this format. If my hypothesis is correct, then this is what we would expect to see happen. Here's a series of infographics made by a team of 2 women scientists who call themselves the Unbiased Science Podcast and can be found on Instagram and many other social media platforms. Is conducting an experiment? What does that really mean in science? Often, the word experiment can be constructed to have a negative connotation. However, experimentation is a carefully planned, organized, systematic, and critical step of solving biological and other scientific problems, answering questions, and making new discoveries. So let's discuss the scientific method and the role of experiments in the pursuit of knowledge. The scientific method is the systematic and organized approach to solving problems in biology, public health, and other sciences. Here, we will provide some simple steps in the pursuit of scientific knowledge. Step 1, make an observation. The observation must be objective and not subjective. There's no place for personal opinions, beliefs, or feelings in science. And this means the event needs to be verifiable by more than just one individual as having happened. Also, science can't study a personal opinion or belief. So, for example, if you believe puppies are cute, science can't study whether that is actually a fact or not, because that is subjective. Someone else might think that puppies are not cute. And science cannot determine which is true and which is not, because neither are true and neither are false. This is subjective. So let's think of an example here. Let's say we observe that your lamp won't work. So you can make the observation, my lamp won't work when I flip this on switch. That is an objective observation that anyone else could come in your room and Also observe and see that it is true that the lamp will not turn on. So then we need to ask a question. How did this phenomenon happen is the type of question we need to ask. So specifically related to the lamp situation, why won't my lamp turn on? So now we need to form a hypothesis or make a proposed explanation for the observed phenomenon. A hypothesis should be as simple as possible, agree with the available observations, be a tentative idea, and be testable. There should be a way to show that it is true or false. So a simple hypothesis to the question, why won't my lamp turn on, is my light bulb is faulty. That's one of the possible answers to the question. Step 4 is to make predictions. So we've proposed a hypothesis that may or may not be true, and then we need to predict what outcomes we would expect if the proposed hypothesis is true. So a prediction based off of our previous hypothesis is if I change my light bulb, then my lamp will work. Step 5 is to test the prediction or experiment. Running an experiment is how we test whether or not our predictions are true. It is critical to change only one variable when testing a hypothesis. This way, you can be certain that only the changed variable may be responsible for a change in outcome. So we predicted that if we change our light bulb, the lamp will work. So then we're going to focus on just changing that one variable, just the light bulb. So we change the light bulb and try to turn on the lamp. Then we need to make more observations and then interpret the results of those observations, ask new questions, and plan next steps. Analyze the results of the experiment to determine if they agree or disagree with the predictions. In other words, we are assessing if the results of our experiments do or do not support the hypothesis. In our example, it's pretty simple. We could find either two possible outcomes. Either the lamp will work or the lamp still will not work. But many times in science, it can take many people with lots of education and experience to actually interpret the results, analyze the results, and make sure that we are interpreting them correctly. So we can then determine if the results and conclusions raise new questions or if a new direction should be explored. It is also important to be transparent about potential biases and threats to the validity. And from here, we can plan the next steps to pursue new questions or further examine observations. Scientific studies usually always have a list of possible errors or why the scientists who were performing the experiments and the studies may have some biases towards one direction or one result or another. The phrase, "it's just a theory," should never be used to refer to a scientific theory. And this is because scientific theories are well substantiated, comprehensive, testable explanations of particular aspects of nature, supported by a mountain of evidence. Even still, a scientific theory does not become a law. A scientific theory can be modified and changed with further evidence. No amount of experimental evidence or testing can prove a hypothesis beyond a shadow of a doubt. A hypothesis gains credibility from positive data that support it. After a substantial amount of testing among many scientists, a scientific theory may emerge. In science, we cannot explain anything with 100% accuracy. Our data either supports or negates our hypotheses and theories. We can build up piles and piles of evidence for ideas, and when that pile reaches a certain point and becomes a scientific theory, it behooves us to take it rather seriously. That is, until someone removes a critical piece from the bottom by showing different mountains of evidence that contradict the first pile. You cannot just bring up one piece of evidence that will completely refute an entire theory. You need to have multiple, or in other words, a whole nother pile of evidence to contradict the first pile. And then we begin a new pile of evidence. All science is merely the current best model. Science is not permanent. There will always be room for change and new discoveries. There will always be doubt, even if it is a tiny amount of doubt. A theory is supported by substantial amount of experimental evidence and is also capable of predicting new phenomena. It is not just a hunch or an idea or an opinion or a guess. The piles of evidence for all the current scientific theories are so high that it behooves us to take them very seriously. So you cannot just dismiss a scientific theory by saying, oh, well, it's just a theory, as if it's somehow not accurate or not shown to be true. So this little student says, I have attempted science. And the teacher, or maybe the judge at the science fair, says, please explain. And the student says, I formed an idea and then discovered I was wrong. And the teacher or judge says there are numerous diagrams. And the student says I was wrong in numerous ways. And then I produced a detailed tribute to my wrongness. And the judge says that is science.